Okay, let's continue the previous section. This is the schematic drawing of mass movement that follow the definition, follow the classification by Varnes back in 1978. Now, from here, we see rotational landslide, translational landslide. We see the block slide. These are all the slide movement. For the block slide, the sliding material consists of large blocks. It can be barracks. But for the translational landslide or rotational slide, the material itself is less coarse, mainly the soil mass. The soil mass slide from the hill slope. For the rotational slide, we see a sliding surface in the form of curve, not necessarily circle. I do not like the term circulational movement because this is not always a circle. A circle, to me, you have to have a center. You have to have the radius. But in reality, landslide less a curve with a perfect circle. It can be non-circle surface. But no matter is a rotational or translational, the slide movement is part of the slide motion. There's a lot of details of this sliding material, but it's beyond the scope of this presentation. It usually take 1 or 2 weeks lecture hours to explain all the details that you may find in reality. So I'm going to skip that. But I truly believe that these three schematic drawing will give you the general idea of the slide movement. Fall itself, just like what I explained in the first part of this presentation, it involves the vertical movement. But for the topple, it is quite difficult to distinguish the fall and topple. But generally, the topple itself involves overturning. For instance, this schematic drawing, we see the topple material accumulate downslope. It used to be at this location. There is a overturning motion involved in topple. But when we visit the site, we only see material accumulate at the toe of a hill. We do not see the overturning motion unless we are at the right moment, at the right place to observe this overturning motion. But we don't want to see that. We don't want to face ourselves in the dangers of the either fall or topple. It is very dangerous. Now, this is another schematic drawing of debris flow. There's a cloud, generate rains, so we need water, we need sediment to produce the debris flow. This is the debris avalanche. Debris avalanche and debris flow. Also, it is difficult to distinguish the debris flow and debris avalanche. But we can, if we really want to distinguish the debris avalanche and debris flow, then we can use the amount of moisture in the debris. If the debris itself is relatively wet, then it flows like wet cement. If the debris is relatively wet, then it will flow down slope. But if the debris is relatively dry, then the motion we call the debris avalanche. The debris itself consists of mainly a coarse material, but if the material consists of fine material, then we call it earth flow. So it is quite easy to see from debris flow, debris avalanche, and earth flow to see the differences of flow, avalanche, and earth flow. The creep itself, as I explained in the previous lecture, creep occurs almost every day. There's no way you can see the actual movement because the movement itself is very, very slow. But when we reach to a site, if we notice a tilting of the telephone pole or any or trees, if you see the telephone pole is leaning toward downslope, or if the tree is leaning toward downslope, then we know that creep is occurring at the site. The very last one is called spread. Spread is very difficult to explain, but I'm going to explain this motion of spread in the other way that we experience almost every morning. I like to have my toast lightly browned, my bread lightly brown toast. When it's done, I like to spread peanut butter on my toast. The motion of spreading peanut butter on a piece of toast is called spread. So when you have material moving downslope and is spread laterally, then this is called lateral spread. Different kind of mass movement involves different speed. So this is the general observation that scientists made in terms of velocity of the movement. Creep itself moves extremely slow. So from the records, scientists observed that the velocity of creeps occur in the range of 1 millimeter per year or 1 centimeter per year. It's very slow, but it occurs almost every day. But on the other end of this spectrum, we see the rock falls. Rock falls occurs so fast. Based on the field observation, the maximum speed can reach to 100 meters per second. 100 meters per second, down to 1 meter per second. This is the speed or the velocity of the falls. Avalanche also. We have debris avalanche occurs in very fast speed, 100 meters per second, or even higher, or even faster than 100 meters per second, and down to 1 meter per second. In the middle range of the spectrum is the mud and debris flow. They move in the range from 1 centimeter per hour up to 1 kilometer per hour. This is how fast debris flow or mud flow moves. Landslide or slump also moves at the similar velocity range from 1 centimeter per minute down to 1 centimeter per day. I hope this information will give you the idea how slow or how fast the mass movement occurs. We can deal with creeps because it moves very slow, but it is very difficult to deal with a rock fall. It's very difficult to deal with debris of launch because it just happens so quickly. There's no way, there's no time for you to escape safely from the site. Erosion starts with a water drop. Water drops hit the soil, create splash. When the splash occurs on the bare soil, little water droplets carry the eroded soil further away from the point of impact. Therefore, back to the general physics, soil forces subtract the resistance. If the force itself is great enough to overcome the resistance of the material, then the material will be displaced. Then we see the displacement of the material. So when the rain hits the soil, generate enough force to overcome the resistance of the soil, then we see the soil particle being displaced, just like the splash. And then we see the motion of the splash. Therefore, for the erosion processes, it involves three processes. One is the detachment. Detachment is when the rain force is greater than the soil resistance. If the rain generates enough force to overcome the soil resistance, then the displacement occurs. Once the displacement occurs, motion initiates. When motion initiates, erosion processes moves from detachment to transportation. So transportation is the result of motion. But the displaced soil particles cannot move endlessly. It somehow, somewhere, it has to return back to the surface because of the gravitational force try to pull the particles in motion back into the soil. Then we see the deposition processes. So for erosion processes, there are three processes involved. One is the detachment, forces greater than resistance. If force is greater than resistance, then there will be a displacement, which is the transportation. Displacement, you have displacement, then you will have motion. Motion represent by this term, by this process is transportation. And at the end, the particle in motion has to return to the surface of the soil. And that process is called deposition. The impact of erosion, I like to express the impact of erosion in this way. Of course, erosion itself generates very, very nice looking, very, very magnificent landscape. For instance, in Turkey, this is the result of erosion. However, the erosion cause problems. For instance, this is the rill. Eventually, it will become gullies. So the impact of erosion, there were three losses. I think there were three losses due to the impact of erosion. One loss is the soil fertility. When the topsoil, which is rich in nutrient, moved by the erosion processes, then it will decrease the soil fertility. When the soil fertility decreases, then the crop productivity will decrease accordingly. When we are unable to produce enough crops for our daily needs, then our life security is in danger. Therefore, there were three losses caused by erosion. One is loss by soil fertility, loss of crop productivity, and at the end, the final consequences of erosion is loss of life security. In order to overcome these three losses caused by erosion, we have to increase in cost, the cost of maintaining the soil fertility. We apply further fertilizer. We even bring the soil from elsewhere to fill the rills, to fill the gaps the rill generates in order to return the soil fertility. Therefore, loss of soil fertility increases the cost of maintaining a cropland. It also increases the sedimentation. We sometimes have to dredge the sediment from rivers, from lakes, from reservoirs in order to maintain the water storage capacity of the reservoirs. All the sediment erode from, for instance, this site in Turkey. All the sediment eroded from the site eventually reach to the rivers. We have to spend a lot of money, efforts to dredge the sediment. So it increased the cost of sedimentation. It also increased the hazard risk. We like to protect our homeland. We like to protect our properties. In order to do that, then we have to increase the cost to reduce the hazard risk. So these are the three losses caused by erosion, and we have to face the three increases to maintain the soil fertility, to maintain the crop productivity, and to secure our daily lives. These are the impact of erosion. So I'm going to share with you a video clip. This is the time-lapse video of a real development. This plot is set at the slope of 9%. We use the rainfall generator to generate a storm with a rainfall intensity of 80 millimeter per hour. The soil itself is clay loam. Now you can see the rill is gradually increase. It's gradually moving upslope. This experiment consists of three individual stages. Let me stop this video and play this video again. Wait. Well, let me finish this. Okay, I'm going to play this. Okay, this is dry. when the soil is freshly prepared. It rains, and you see the runoff generate on the soil, generate on the surface, and you see the runoff gradually concentrate. Rio starts to move upstream. This is the later on you'll see the soil become relatively wet. This is the second stage. The soil is relatively wet. We call it wet run. The soil is relatively wet. And then later on you'll see the very wet run. The soil is almost reached to the saturation. The observe the reel here. See? Here's another reel develop. Okay, let me play this again. Dry run. Rainfall. Runoff generate. Concentrate. And reel develop. Reels moving upslope, upstream, like tree branches. All the sediment moves downstream. Reel continuously moving upslope. And here we call it haircuts. The haircuts is cutting the slope. And reel develop continuously from the downslope. Here you see a reel. Right about here, you see the reel. And this reel will not only widen the width of the reel, it will continuously deepen the reel. It will cut vertically into the soil. It will widen the width of the reel. Eventually, you will reach to the stage of gully. Erosion, the process of erosion involves, it's a function of erosivity. It's a function of erodibility. Both erosivity and erodibility works together to create erosion. Erosivity is a forces. We need external forces to generate erosion. The erosion, the force itself has to be great enough to overcome the resistance. And the resistance is the erodibility. Pretty much like the first slide in the previous presentation. If you still remember, we try to stretch a rubber band. We apply forces to both ends of rubber band, and the rubber band generate resistance to fight against the external forces. So when the forces is greater than the resistance, then the displacement starts. Now, for the term of erodibility, erodibility can be further classified into two parts. One is the internal properties of the soil, mainly the physical properties. Soil is gradually developed through weathering from the bedrock. So the bedrock, through weathering processes, it becomes the soil. There's no way that we can change the soil property unless we apply soil improvement. Otherwise, there's no way we can control the physical property of the soil. The stronger the soil, the stronger the soil, the lower the erodibility of the soil. Some soil is so strong that if you apply force to the soil, for instance, a wind or water, you apply the water, you apply the wind to the soil. The soil itself, if it's strong enough to fight against the force, then no erosion will occur. But if the soil is very weak, a little force applied to the soil, for instance, a light wind blow through the soil surface, it will generate the motion of the soil particle. Then we call that wind erosion. If we apply rain to the less resist soil, then water erosion will occur rapidly. But we cannot change the internal property of soil. However, humans apply external effects to the soil. The external effects include slope steepness, slope length. Sometimes we like to develop our hillland based on our needs. So we cut the slope from a very relative flat slope into steep slope. Let me draw a schematic diagram if it's possible. Let's change this to that. Okay. Say for instance, this is the original slope. For some reason, we like to build a road through this slope. So we cut the slope. Where are you? It's not easy to find. Oh, here you are. Okay. Say, for instance, we want to build a road through this hill slope. So we cut the slope. We cut the slope and we remove the soil and we build a road. Oh, and we build a road. This is the foundation of the road. We cut the slope. We cut this off. So we cut this off. And the slope itself becomes steep. The slope becomes steep. Here, the slope becomes steep. When the slope becomes steep, then the soil material will become less stable. Therefore, we have to build a structure at the cut slope to prevent this mass from sliding. So, in order to fulfill our needs, we need to build a road. We cut the slope, we move the material, and we build the foundation of the slope, foundation of the road. That changed the slope steepness. Of the slope. That is the external effect that we make this soil less stable. And we also make the soil less resistant against the external forces. There's another external effect. It's the land use, either agricultural land use or non-agricultural land use. We cut the forest off. We clean cut all the forest in order to fulfill our agricultural activities. That change the soil cover and make the soil less resistant to forces and make the soil highly erodible. There's another effect caused by the external effect is the conservation measures. So all these will change the soil erodibility and make the soil less stable and make the soil highly erodible. Now, of course, that we live on the surface of Earth. We have to develop social development is unavoidable. So we build settlement, we build roads, we build other infrastructure. We have to grow crops, we have to raise cattle. But all these activities, without conservation measures, that will make the situation worse. It is estimated that 1 billion tons of valuable nutrient in topsoil are lost to erosion every year. 1 billion tons per year. I like to use this slide to draw your attention. A former president of the United States, Roosevelt, he wrote a letter to state governors on the Uniform Soil Conservation Law. And he said, a nation that destroys its soil destroys itself. So Roosevelt already recognized the severity of erosion problems. FAO also make an announcement, say every 5 seconds, the equivalent of one soccer field is lost due to soil erosion. Every 5 seconds, one soccer field is lost due to erosion. In other words, every 5 seconds, the area of erosion covers almost one soccer field. It is a very severe problem. And back in 2014, December the 5th, a statement made said that only 60 years of farming left if soil degradation continues. This is back in 2014. This statement warns us that if we let the soil continuously degrading, then we will have no land to farm 60 years from 2014. Now it's 2022. In other words, if this statement is correct, then we have only 50 years, 52 or less than 52 years left. And if there's no land that we can farm, there's no land that we can grow our crops, raise our cattle, then food security will be a major problem. Main causes of erosion by human are 5 categories: deforestation, overgrazing, agrochemicals, tillage technology, tillage techniques, construction, and recreation activities. These are what we are continuously harming our earth: deforestation, overgrazing, agrochemicals, tillage techniques, construction, and recreational activities. Now, if we look at the world as a whole, this is a really, this is the information that um, I gathered back in 1990s. Back in 1990s, uh, a group of scientists, they look at the cause of soil degradation for the entire world. 35% were due to 35% of soil degradation was due to overglazing, followed by 30% deforestation, 28% by agricultural activities, 7% by overexploitation for fuel woods, and 1% by industrialization. This is for the entire world. In Taiwan, if we consider Asia, for Asia, 40% deforestation, 27% agricultural activities, 26% is due to overglazing. So if we look at Europe, Africa, North America, Central America, South America, you see Africa 49%, which is overglazing. For North America, Central America, and South America, agricultural activities. Now, I like to bring this back to your attention again. Rill and gully. Rill is caused by concentration of surface runoff. There's a lot of research involves in the initiation or the the formation of gullies. I'm not going to go into the detail. Instead, I'm going to show you a video clip again. This is the this is a experiment that we conduct back in 2016. It's a time lapse video clip. We first prepared this plot with a trench. This trench representing a gully, a small gully. Now and then we ran on it. The rain starts, runoff generates, rill start moving upslope. Notice both sides of the rill of the gully. See, we have slump on both sides. Gully continues, rill continuously moving upslope. See, here's another slump. Here's a slump. Slump at the haircut, at the head of the gully. And if you look at this video clip and also compare what you see on the left-hand side of the slide, this is what happened. Okay, here we introduced the flow from the upstream. Okay, let me play this again. Runoff concentrate in the gully. Rill move very fast. Here's the time. It moves very fast. And you have slump on the sidewall of the gully. Excuse me. Here's a slump. Look at the time. Now we're going to introduce the flow from the upstream. Here, flow from the upstream, from the upper watershed. me play this again. Here's this flow from the upstream. And the original rill start migrate laterally, and from some time during this video you see the meandering. Here you go. See, you see the meandering of the stream, of the gully. Okay. When the rill develop this way, it is almost impossible. Not really impossible, but it will cost money to refill this gully with the soil. It will cost money. Okay. So what can we do? We need to minimize. We need to minimize. There's no. We have to minimize the external effect so that the resistance of soil maintain its original stage. We need to change the way we use our land. The most importantly, we apply conservation measures to the places that we alter the soil erodibility.